In this lesson, we are going to start a new unit about exponential functions. Now, in general, an exponential function, as we are going to talk about later, is given by equation f of x is equal to a b exponent x. Any equation where the variable is in the exponent is called exponential function. Now, a and b are real numbers that we are going to specify the properties of a and b later on in future sections. But at the moment, we would like to talk about exponential growth. What exactly is an exponential growth? We define an exponential growth as a pattern in which every term is multiplied by a constant either greater than 1 or between 0 and 1 to produce the next term. Now, if that number is between 0 and 1, it's not going to be exponential growth. In fact, it's going to be exponential decay, which is going to be the topic of the next video. But at the moment, if every term is multiplied by a number which is greater than 1, we call this one exponential growth. Give you one example of exponential growth. Look at the table of value like the following. When x is 1, let's say y is 2. When x is 2, y is 4. When x is 3, y is 8, and so forth. For instance, when x is 4, y is 16. If you look at the ratios of the terms here, 4 divided by 2 gives you 2, 8 divided by 4 gives you 2, 16 divided by 8 gives you 2. Every term is the product of the previous term times a constant. In this case, the constant is 2. This is what we call an exponential growth. Now, if you start plotting an exponential growth table of value, you will get a graph, something like this one, which you can see that the graph increases at a constantly increasing rate. To show you what it means is that remember that a horizontal line has a slope equal to 0. A vertical line has a slope which is undefined. We can call undefined something like infinite. Now, if at any point on this graph I draw a line which is tangent to the graph, you can see that the slope starts from 0 and it goes up and it's increasing until it gets to undefined, which is about infinity. This type of graph represents an exponential growth function. Now, there are a couple of properties of exponential growth function that we are going to discuss right now. The first one is that as your independent variable x is increasing by a constant amount, the dependent variable increases by a common factor, that ratio that we did in the previous example, which was 2. So every term is multiplied by 2, you get the next term. The graph increases at an increasing rate, as I showed you on the graph. The slope of the lines which are tangent to the graph, it starts from 0 when the tangent is parallel to x-axis, and it increases until it is parallel to y-axis, which is infinite. Now, the other important fact about exponential growth is that the finite differences, they show a repeating pattern. The ratio of successive finite differences is constant. I'm going to show you this observation for the previous example we did. Consider the following table of values. For x equal to 1, y is 2, x is 2, y is 4, and so forth to x equal to 6, y is 64. if you look at the first differences, okay, which is the first finite differences here, you can see that 4 minus 2 gives you 2, 8 minus 4 gives you 4, 16 minus 8 gives you 8, 32 minus 16 gives you 16, 64 minus 32 gives you 32. The second differences is going to give you 4 minus 2 is 2, 8 minus 4 is 4, 16 minus 8 is 8, 32 minus 16 is 16. If we continue this way, the third differences is going to be 4 minus 2 is 2, 8 minus 4 is 4, 16 minus 8 is 8. Now, if you look at the ratios of the first differences, 4 divided by 2 gives you 2. 8 divided by 4 gives you 2, 16 divided by 8 gives you 2, 32 divided by 16 gives you 2. If you go to second differences, 4 divided by 2 gives you 2, 8 divided by 4 gives you 2, 16 divided by 8 gives you 2. If you go to third differences, 4 divided by 2 gives you 2, 8 divided by 4 gives you 2. And also if you go and look at the column representing y, you can see 4 divided by 2 gives you 2, 8 divided by 4 gives you 2, and so forth. All of them are 2. This shows you the repeating pattern. The ratio of successive finite differences, either first, second, or third, is a constant, and that constant in this example is 2. The first example, we have a bacteria which grows such that it triples in number every day. On the day that Roger begins observing the bacteria, a sample has a population of 100. We are supposed to find the population after each of the first 4 days. So let's represent D with day number and P for population. At D0, meaning initially we have 100. Day 1, we are going to triple this one, so we are going to have 300. Day 2, we are going to have triple this one, 900. Day 3, we are going to have to triple this one, 2700. And day 4 is going to be triple of this guy, which is going to be 8100 bacteria. Now we are supposed to write an equation which represents this situation. I'm going to write the first one, the population, as really 3 exponent 0 times 100. Because 3 exponent 0 is 1, 1 times 100 is going to give me 300. The next one, I'm going to write 3 exponent 1 times 100. Because 3 exponent 1 is 3 times 100 is going to give me 300. For the next one, I'm going to write it as 3 exponent 2 times 100. The next one, 3 exponent 3 times 100. The next one, 3 exponent 4 times 100. Now, if you look at the pattern, you can see that the exponent here is really the day number. So when day is 0, exponent is 0. When day is 1, exponent is 1, and so forth. So I can write that the population is equal to 100 times 3 exponent d, where the d is the day number and p is the population. The next part of the question says graph the relation. Remember the relation that we found was p is equal to 3 exponent d times 100. So I'm going to again make the table of value. This time is d and p. When d is equal to 0, we get 100. When d is 1, we get 300. When d is 2, we get 900. And when d is 3, we get 2700. So our graph approximately is going to look like If this is D, this is the population, day 1, day 2, day 3, and our population goes 100, 300. So if I assume this is, let's say 100 is here, day 0 is 100, which is here. Day 1 is 300, so I'm going to go 3 units up, so 300 is here, but it's day 1, so it's going to be here. Day 2 is going to be 900, so assuming 900 is somewhere around here on the top, we're going to get a point here. Then if we connect them using a smooth curve, we get something like this graph, which represents the graph of p equal 3 exponent d times 100. The next part of the question says, assuming this trend continues, predict the population after 1 week. So this, we know that p is equal to 100 times 3 exponent. 1 week is 7 days. If we use the calculator, we are going to find that this is 218,700. The next one says find the number after 2 weeks, so we're going to say p is equal to 100 times 3 exponent d. D is 2 weeks, which is 14 days. If we use your calculator, we will find that this is 478,296,900. The last part of the question says describe the pattern of finite differences for this relationship. The first difference is 300 minus 100 is 200, 900 minus 300 is 600, 2700 minus 900 is 1800, and 8100 minus 2700 is 5400. The second difference is 600 minus 200 is 400, 1800 minus 600 is 1200, 5400 minus 1800 is 3600. You can see that the first and second differences are all different. So this is not a linear function, obviously. And it is not a quadratic because second differences are not the same. But if you look at the ratio, 600 divided by 200 is 3, 1800 divided by 600 is 3, 5400 divided by 1800 is 3, 1200 divided by 400 is 3, 3600 divided by 1200 is also 3. But you can see that the ratios are all end up to be the same. Even the ratio of the p-values here, if you look, they are all 3. So this obviously represents an exponential function.